Okay, so screwy week this week because of campus day. So no class Wednesday. And since one of the labs is on Wednesday, we're not going to have that lab. Thursday lab's also not going to have lab Wednesday. So no class for us Wednesday or Thursday. That also means the homework is going to be due Friday, and we'll have our normal quiz now. Any questions on schedule? In that case, let's review from last time. So we were talking about electromagnetic induction, or magnetic induction, I should say. And we said that we had two laws. We had Lenz's law, and we had Faraday's law. And both of these had to deal with what direction do we induce a current if you have a changing magnetic flux. Give you some practice so you can still remember your right hand rule. So you have a magnetic field going in through that loop, and it's decreasing. Lenz's law tells you the direction that the current is going to be induced. So if you have a magnetic field going in and it's decreasing, what direction of current would you get? Clockwise or counterclockwise? Around this line or clockwise, let's say. So you have magnetic field pointing in and it's decreasing. So that means I want to have some magnetic field pointing in to make up for that. And the way to do that is to get the current going clockwise around, so I agree, it should be clockwise in this case. This would be your induced current. And then, that told you the direction of the current. Faraday's law tells you how much electromotive force you're actually going to get out of that. That's just equal to the electromotive force that you get is equal to the change in flux divided by the change in time. So how fast your magnetic flux is changing. Any questions left over from last time? Okay. If not, we've reached kind of a weird pinnacle in the course. Because we can now really start talking about electromagnetic waves. Now, we talked about waves last semester, but we just kind of said by fiat that light is an electromagnetic wave. But we hadn't even talked about electricity and magnetism at that point. So we want to know, what does it mean to actually be an electromagnetic wave? And we're going to talk about that today. Today's going to be a little bit of history in today's class. The first bit of history goes back to about 1800. With a guy named Herschel. By the way, I'd highly recommend that you watch the Cosmos series from last year. There's a cartoon about this guy in there that kind of gives the story behind this. We're just going to do kind of the Cliff Note version of this today. But Herschel was a scientist. He did this experiment. Basically, here's the sun. The sun's giving off rays in all directions, and he shines some light through a hole. The light that goes through that hole reaches a prism. And as I'm sure most of you know, A prism will separate light into different directions, or into different colors rather. So we might get some red over here. We'll get some orange. Some green. Some blue, and then you'll get some violet. Hear people picking out lots of different colored pens. And the question Herschel was really interested in is, all right, we know light is made up, white light is made up of all these different colors because we can separate it with a prism. And we know, or we have this idea that light has some energy associated with it. So how much energy is associated with each color of light? We want to know which color has the most energy. So Herschel did kind of an interesting experiment. He said, all right, I've separated the different colors. I'm going to shine those different colored lights on different thermometers and see which one gets the biggest temperature. So the light that has the most energy should make the temperature rise. So what he did, he said, all right, we've got a purple. This is the thermometer that's in purple. This is the thermometer that's in blue. This is the thermometer that's in green. This one's in orange. This is red. And you've always got to have some control group. Make sure the temperature is not rising for just any other reason. And then this one was in the shade. And so he wanted to know which color had the biggest increase in temperature. Right? So light is delivering energy to this. That energy will get converted to thermal energy. Which of those thermometers is going to heat up the most? What's that? All right. How many of you say red? Who says red? One person says red. How many people say orange? Somebody says orange. How many says green? How many say green? One person says green. How many people say blue? How many people say blue? How many people say purple? Pretty much everybody else. Anybody say shade? It's shade. How does that work?
Because it was always in this one.
It does, well, yes. But why, if I'm putting it in the shade, why, this is something Herschel was very confused about. How can you explain how something that's not getting any light at all is going to have the most increase in energy?
It did not change the temperature at all.
No, it had a temperature increase. It had the biggest temperature increase. The shade is the one that got the hottest. Well, the tricky thing is, it's not actually shade. What Herschel realized, there must be some invisible light, light we can't see. There must be some invisible light that's causing that temperature increase. This is the infrared. Yeah, question?
I was just going to ask if, like, in this example, if light and heat are the same thing.
I would say they're not the same thing. So the light is its own particular form of energy. I would say they have the same energy. So the light energy is getting turned into thermal energy. But I would say light and heat aren't necessarily the same. Light just happens to be converted to heat when it hits the thermometer. So until it hits the thermometer, it's different. When it hits the thermometer, it gets converted to heat. Good question. Other questions? So this was about 200 years ago. So already, even back then, they were getting inklings that maybe red, yellow, green, and blue, the colors of the rainbow, weren't the whole story when it came to work. There was another example of this. This one came quite a bit later. This was in 1895. Rontgen did this experiment. This one's a little bit more directly correlated with electricity because it involves actual electrons. Rontgen took a high voltage source. This was in a tube. And basically what he did, using that high voltage source, essentially shot electrons out. And some of those electrons went streaming past and ended up colliding with the wall. They smashed into the wall of this glass tube. And whenever the tube was on, Rontgen noticed something kind of interesting, is that even far away from the tube, on the wall in the back, you would get this sort of glowing coming from the wall. So he's like, that's weird. Whenever I turn my instrument on, it starts glowing really far away. So he's like, all right, well, let me try to get rid of that glowing. So he put some material in front, and it turned out, even with the material in front, it was still glowing. So what Rontgen had actually discovered there is that when your electrons come smashing into that glass, they get accelerated a whole bunch. And they start to emit radiation. And this radiation can penetrate through maybe not most. Radiation can penetrate through a lot of different materials. Rontgen didn't know what it was. They knew about different types of radiation. They knew about cathode rays and other things. By the way, this was a cathode. So these were cathode rays that were generated. But since he didn't know what type of radiation it was, much like in math class, he just called his unknown variable x, and he called it a mixture. It wasn't very long after that he tried putting other things in front. I believe the first picture he took with X-rays was of his wife's hand. But if you look up X-rays, you can see the very first X-ray was, or one of the very first anyway, was a picture of a hand with a ring on it. And they very quickly realized that whatever this type of radiation was, you could use it to do medical diagnosis. All of a sudden, you didn't have to worry about, is my arm broken or is it not? You could just use this X-ray to take a picture that could see inside your body without ever cutting yourself open. So this X-ray was this weird, invisible radiation could penetrate objects. Some objects. Not all. Has a hard time making it through bone. It can penetrate a lot of soft tissues. By the way, one of the questions I got in the reading was, are all types of radiation dangerous? First of all, why do we what's the source of the word radiation? Say it? So it's something that radiates out, right? So radiation just means anything that's radiating out. So it could be, a light bulb is a source of radiation. So not all sources of radiation are dangerous. That's your etymology lesson for today. Etymology? Is it etymology or entomology? So you must be an etymologist, since you know the difference.
Yes.
Could have also asked for my, he's my go-to bug guy. Okay, so that was the discovery of X-rays. Now Maxwell had seen a lot of these experiments. The X-rays actually came a little bit later. But Maxwell was more of a theoretician. He's more of a mathematician. He's somebody who likes to play around with equations. And he had come around at just about the right time for the physics world, because he made what was probably, in my opinion, the most important discovery, I would say the most important human event in the 1800s. This was around, I'm getting the dates right, around 1873 or something.
So after?
It was actually before Rontgen made his discovery. But people had known about electricity and magnetism for quite some time. They had already known about induction. Faraday had already done his experiments. Faraday and Maxwell were both in England at around the same time, more or less. And so Maxwell knew that if I have a wire, and I have a changing magnetic field in that wire, changing magnetic field, he knew that you got some current going around. You got some electromotive force, and that electromotive force produced some current. So Maxwell said, we've got this changing magnetic field producing current, pushing charges around. Well, I know that I know electric fields push charges around. So it's kind of like this changing magnetic field makes an electric field. Makes an E field. And he was able to look at a bunch of equations, all the equations that we looked at, all the different electricity and magnetism equations. And we said, all right, well, what happens if a changing electric field also makes a magnetic field? What happens if the reverse is true? So we know this. What if a changing E field makes a magnetic field? I know magnetic fields create electric fields. Changing magnetic fields create electric fields. What if a changing electric field makes a magnetic field? Or, makes a magnetic field. So he basically just made up an equation that looked at changing electric fields and guessed what would happen if it made a changing magnetic field. And then a little bit of math later, he was able to combine the different electricity and magnetism equations to come up with something that was kind of interesting. Again, there's no experiments done with this. This was mostly just him being good at math. So here's Maxwell's math. I'm not going to do all the math because you need to look at this work, but I'll give you the end result. came up with something that looked like this. There was a constant in here, which I'll call C. And then there's, if you do not know what the d by dx means, don't worry about it. It's a calculus term, it's a derivative. Unfortunately, there's no way I can write this equation without using some calculus. You don't have to worry about the calculus part, though. But basically, he said, if I take the second derivative of the magnetic field, and the second derivative of the magnetic field with respect to time, so one with position, one with time, I get an equation that looks like this. And then I get another equation that looks like this. I get the same equation for the electric field. Any people who have taken lots of math classes, have you ever seen those equations before? Perhaps with different variables? They have a name, these are called wave equations. We talked about sinusoidal waves last term. Those calculus equations, the solution to those calculus equations are the wave equations we went over last term. The sine and cosine equations we talked about. And it turns out that that constant is just equivalent to the wave speed in that wave equation. And when Maxwell worked it out with all of the different electricity and magnetism equations, the constant turned out to be very simple. It just depended on two other constants. The electric constant and the magnetic constant that we talked about. Permeability and permittivity. So Maxwell's guess that a changing electric field creates a magnetic field. If you make that assumption and then you do the math out, you get these wave equations. And the wave equations predict a wave speed that's just related to the two electricity and magnetism constants that we have. And if you plug in the values of these epsilon naught and mu naught into that equation, it turns out you get a number that's equal to 3 times 10 to the 8 meters per second. Just by doing, no experiments here, just by doing math, you can figure things out. So, let's see if we can actually make some sense out of this. The thought is this. So I've got a changing magnetic field. That creates a changing magnetic flux that makes current around the loop. But that changing magnetic field, the reason I get that current is because if I have a changing magnetic field this way, I will get a changing electric field in the other direction. So magnetic field this way, changing electric field going around it. Now Maxwell says, all right, now you've got a changing electric field. Well, that in turn is going to create a changing magnetic field around it. And so you have these two fields that are kind of changing with each other, that are going back and forth. First it's an electric field, then it's a magnetic field. Exchanging energy between those two fields. So if that's the case, if a changing electric field creates a changing magnetic field, and a changing magnetic field creates a changing electric field, then it's basically the song that never ends. It's electric field becomes magnetic field becomes electric field. It goes back and forth forever and ever. And it follows this sort of self-sustaining way. By constantly switching back and forth between these two, the prediction is that we're going to get an electromagnetic wave. Well, how do we test that? Well, one thing we can do is we can look and see, does light really travel at 3 times 10 to the 8 meters per second? And it turns out that experiment was already done. In fact, it was done about 200 years before Maxwell. A guy named Romer. 1600s were an interesting time in science. So here's the Earth. Here's Romer. At this point, Galileo had invented the telescope. So you could look off, and you could see things that were much further away than we could before. So you were able to see Jupiter. And what's more, you could see not only Jupiter, but you could see Jupiter's moons. You could see really, really well some of the telescopes that were made at the time. So that's one of Jupiter's moons. That time period really created a whole lot of unrest. Because if you're one of the earlier astronomers, and you're like, oh, turns out we were wrong. The Earth isn't the center of the universe. The Earth goes around the sun, and the sun's not even the center of the universe. People are like, witch, burn him. And so it was a dangerous time, especially since most, Copernicus and people like that, most of them were, if they were smart enough to figure this out, they did it with math and looking at how the Earth went around the sun. And today is a pretty good example of that. If you try to explain something to somebody with math alone, and they don't have the math background to get it, they're just going to assume it's not true, or you're making things up, especially if it's something that sounds crazy, like the Earth goes around the sun. Weird. But when Galileo came along, he invented the telescope. You can actually see the moons going around Jupiter, right? You look at it every night, and then you see where the moons are, and you're like, oh, clearly not everything goes around the Earth. This is going around Jupiter. But Romer even went beyond that. Romer noticed something kind of interesting, is that if you look at if you time where the moon is in its period around Jupiter, what you find is this. Sometimes the moon is ahead of where it should be. Seems like it's going too fast. Usually that's when it's closer, when the moon is on your side, it seems to be a little bit ahead of where it is supposed to be. Other times it's behind where it should be. So if the moon is on the far side of Jupiter, it's behind where it should be. If it's here, it seems like it's ahead of where it should be. So it seems like it's sped up in time. On the other end, it seems like it's slowed down in time. That seems a little strange, but it actually makes perfect sense if you assume light takes some time to reach it. Some time to reach the Earth. So that when the moon is over here, it's traveling a further distance than when the moon is close by. R2 is smaller than R1, so it's natural that R2, the moon is going to seem a little bit ahead because it doesn't take as much time for the light to reach it. At R1, the moon is further away, so it takes more time, so it seems like the moon is a little bit behind where it should be. So even 200 years before Maxwell, they already knew, because Romer figured out, his estimate was actually quite a bit off. But they already had a way to measure the speed of light and figure out it was about this big. Again, the numbers just popped out of electricity and magnetism. They're just the constants that we've been dealing with. So that's a good sign. That's a sign that Maxwell's on the right track. But really, we want a direct experiment that can relate electricity and magnetism together in light. Very different. On the surface, they seem like very different phenomena. One things we see, electricity and magnetism, is things that we normally don't think we can see because charges are too small. But it seems like we've got a good theory. Before I go on to how you can actually test this, let me stop here and take questions before I do. Questions so far? Okay, in that case, 1895 comes around, and this guy Hertz shows up. Hertz, I believe, is also the same person who the frequency unit Hertz is named after. And he wants to test Maxwell's theory. So Hertz's thought is, all right, well, if changing electric fields create changing magnetic fields, and that makes an electromagnetic wave, which is equivalent to light, I ought to be able to make electromagnetic radiation just using circuits. Circuits like those that are in your cell phone. So he had this setup. Again, he used a high voltage source. And we had a couple of instruments over here. Basically, there were these two metal balls that were next to each other. And then far away, he actually used to do this experiment for his students. Far away, he put a ring, or part of a ring, actually. It was a ring, except for there was a little bit of a gap between two metal balls. A very short gap, a couple millimeters, all the way across the lecture hall. So you can imagine he's got a high voltage source on one side, and he's got another loop that's all the way across the room. So high voltage source on that side of the room, a disconnected loop on the other side of the room. And what this high voltage source would do is it would basically make a spark. Make an oscillating spark actually. So you'd see what looked like little bits of lightning just kind of jumping back and forth across those two electrodes. And then all the way across the room, what you'd see over here is you'd see a little induced spark. Every time there was one over there, there'd be a little induced spark all the way across the room. Very far away. So what was going on? Every time you make a spark over there, you end up getting some sort of wave that comes this way. It's a wave, partially an electric field, which I will draw straight up and down. But you also get a wave in magnetic field. You never have the electric field wave by itself. You've also got to get a wave in magnetic field. And this is hard to draw. But the magnetic field wave is perpendicular to the electric field wave. Oops. As I said, hard to draw, especially when you screw that up. And that magnetic field wave is going to create a changing magnetic flux in this loop. What happens what do you get when you get a changing magnetic flux in a loop? What do you induce? Current. So the current wants to go around this loop, but it realizes it can't get from here to here, so that's why you get a little spark. Electrons jump from one side to the other. So this was a definitive statement that said, all right, if I produce electromagnetic radiation, if I produce electromagnetic waves here, I can control with electricity and magnetism, I can control what's going on in the circuit. I can make invisible waves, or possibly visible if it's in the visible light range, but I can make invisible waves that will travel and send signals across space that can be recorded, and you can use that to do useful things. So it turns out that these were electromagnetic waves in the radio region. And Hertz really only took it this far. He had to wait for Marconi and some other people to come along and actually invent things like radio, other more practical reasons. Hertz actually died very, very young for some tragic reasons. I won't get into that too much here. But this is the basis behind how your cell phone works. It's the basis behind how any wireless internet or wireless technology works. What we're doing is we're sending invisible radio waves into your devices, and they're just having currents induced to them. Those currents can contain signals. The signals could be a YouTube video of a cat falling off a table. It could be signals playing Katy Perry. I don't know if you guys listen to. It could be music coming into your car radio. It doesn't really matter. We can encode information in these invisible electromagnetic waves. We can also encode information in terms of visible electromagnetic waves. I'm looking at you guys right now. How do you encode information?
I don't quite understand how it works.
That's a bit more complicated than I'm really prepared to get into now, but let's just do a simple example. Let's say you are smart and you can design a electromagnetic wave that is in the same shape as a sound wave. What's your favorite song? Hey Jude by the Beatles. Okay. Let's say you record Hey Jude by the Beatles, and then you output an electromagnetic wave that has the same peaks and valleys that the sound wave you would get from Hey Jude comes. And then I send that into here. Now if I connect this to a speaker, possibly with some amplifier, I can get a one-to-one match between the electromagnetic wave and the sound wave. Now it's a bit more complicated than that. Why can't I just do that with radio? Like your car radio? Because there's a bunch of different channels, right? So it takes a quite a bit of engineering to get beyond just sending a single signal and to be able to send a bunch of different signals, each of which, so I can tune to NPR and listen to news, or I can tune to the country music station, or I can tune to whatever your favorite music station is. You can tune to that and listen to that without having interference from other radio stations. But that's just a matter of just engineering the different circuits. Fundamentally, we've already solved the problem right here, at least from a scientific perspective. More questions? Yeah.
This is a little far off, but so
I like far
saying
off.
like a home audio system, you got like your main system, and then you got amplifiers that run wirelessly. So you're going from your main system to amplifiers, and then from your amplifiers to your speakers, you have to have cable. Why do you have to have like wireless and then non-wireless to run your speakers? Is that because that has to have the current running through it to power it?
Well, you do need power. So if you have a battery, you could have wireless speakers and that would be fine. You could, I mean, if you have very, very strong waves, you could use the waves to actually create power too. That was something Nikolai Tesla, the same Tesla that's named after magnetic fields, he had lots of weird gadgets for things, but one of the things that he claimed to have invented, and then nobody's ever been able to verify it, was a way to basically for everybody to have wireless power. He was going to build giant towers that would create oscillating magnetic fields, so that you wouldn't need to plug anything in, everything would be wireless. It turns out the magnetic fields that you need for that are much, much bigger than is useful or healthy. But in principle, that even power can be transported wirelessly.
Okay, so like, you have to plug the amplifiers in, and that's a wireless connection. So is the only reason that the speakers to the amplifier are wired is that because power?
I think it probably depends on the model, but I suspect so. Usually, I mean, power is a lot harder to transport than just the signals. So I would say that's probably the case, but it depends on from system to system.
How could you transport power? Isn't power essentially just energy?
It is.
And so wouldn't that energy have to come from somewhere?
Yes. Well, there's energy in the electromagnetic wave.
Yeah, but I guess I would assume that along the way it's losing some of that energy.
Oh, well, it certainly is. But, you know, take for example, solar energy, right? If I put a solar panel out right now, the sunlight that's hitting the Earth has 1,400 watts of power for every meter squared. So, you know, your laptop takes, if you have a relatively new laptop, takes like between 15 and 30 watts of power. So, you know, 1 meter squared of sunlight gives you 100 times what, 100 times what you need. So light can have a lot of energy, but it has to be very, very intense light. Yeah.
So why can't they store solar energy?
Well, that's more a question about batteries than solar. And you can't store solar energy; it's just expensive. So it's just that's a matter of the cost. So what you do is you convert the sun's energy into chemical energy, and then you save the chemical energy. But it turns out that's just expensive.
Solar panels are only like 10% effective.
Well, whenever you're converting energy from one form to another, well, not even so much that you're using, I mean, energy is a very slippery beast. So if I have, let's say I have a glass of energy here, it's my solar energy, this is just a stupid analogy. But if I try to pour energy from one form to another, it turns out humans are like drunks when they're pouring energy from one form to another. A lot of it gets spilled in other places. So it turns out it's just very hard to do things with 100% efficiency. More questions?
This is more to do with the solar power than the electromagnetic waves. But have you heard about the proposal to have roadways that are made with solar panels?
Yes.
And that light their own lanes?
I haven't heard about them lighting their own lanes, but I do know about the solar roadways project. And if you calculate how much energy they'll produce, it's actually pretty close to being what we need to power the
Wouldn't
US.
it pay for itself
Yes.
fairly soon?
Well, yeah, I mean,
after they're built.
a lot of things will pay for themselves fairly soon, but the upfront cost is such that nobody has the money to pay to get it started anyway. But yeah, that's one of those projects that is actually based on pretty good science, I would say, at least from my simple estimates of it. Okay, I want to point out a couple of things about how these waves travel now. Because there are some rules that are kind of important. We're going to pay attention to some of them. One of the rules is something I tried to draw over there, although it's a little bit tricky to see from my drawing. It turns out that the electric fields in the electromagnetic waves, and the magnetic fields and the electromagnetic waves are always perpendicular to each other. So if I have an electric field that points up like this, I might have a magnetic field that's pointing out like this. And it turns out you've got to do the right-hand rule to figure out which way the light is going. So the way it works is if the electric field is pointing up, put my fingers pointing up, and I want to curl my fingers to the magnetic field. If you do that, then your thumb will point in the direction that the wave is moving. That would be your wave velocity.
Repeat that one more time.
Yep. So it's similar to the V cross B gives you the force. Take the electric field, put your fingers along it. Curl your fingers to the magnetic field. So there's only one way I can curl my fingers to the magnetic field. And my thumb points in the direction that the light is moving. Let's try that. Say the electric field is up, and magnetic field is this way. Which way would the light move? Inward. Say the electric field is this way, magnetic field is that way. So the electric field, magnetic field, and the speed of light are all perpendicular to each other. Or velocity of light, I should say. There's another part about this that's, you probably heard something about if you've taken chemistry before. Have you guys heard chemistry people? Have you heard of plane polarized light before? Plane polarized light? No? Maybe? No? Plane polarized light basically just means that the electric field is just going up and down in a plane. So it turns out light has different polarizations. So I could talk about polarization up and down. I could talk about polarization left and right. I could talk about it being polarized at a 45-degree angle, or any angle for that matter. We could also talk about unpolarized light. So for the most part, light coming from the sun, from light bulbs above your head, that light is unpolarized, which means basically every possible polarization of light is coming out at you. But it turns out there's a way to split up the different polarizations. So I have over here, I have a crystal. This crystal is called calcite. It's just a crystal, like a normal crystal, like salt is. But this particular crystal has a unique property. It has the property that it can separate different polarizations of light. So here I have a sheet of paper with just a line drawn on it. And I'm going to, if I can put this on. There we go. I'm just going to put this little piece of calcite on that line, and you'll see what happens if I orient that the right way. You can see all of a sudden you get two lines. And as I move it back and forth, you can see those lines go in and out. So it turns out the direction of the crystal, the direction that I hold the crystal, can separate two different polarizations of that light. Now, calcite is one type of crystal. So the two lines I'm seeing have different polarizations. Turns out one's polarized horizontally, one's polarized vertically. The light is, I should say. I also have a polarizing filter. So this is the same thing that you have in things like polarizing sunglasses. So the polarizer basically cuts out one type of polarization. So what will happen when I put this polarizer over my calcite. Okay, let's see. So one of the lines goes away. You can't see that remotely, can you?
Sort of, kinda.
Kind of. I'll pass this around in a second. What you should see is that the lines will go away, and it'll switch back and forth as it'll switch back and forth as you move the polarizer around. I'll pass that around in a second. But first, actually, well, I'll pass this around and then I'll steal the polarizer back. So I need it for one more demonstration. I have another demonstration here. This one you might have to gather around for because I don't know how well you're going to see it from that far away. I will try to orient this so that most people can see it. But I don't know how we're. You guys on that side see?
Question.
Yeah.
Is this how, you know those like little card things or something that are like you like move it back and forth and you can see different.
Yeah.
Is that how this works?
I'm not actually sure how those. I know exactly what you're talking about.
Well, like the little cards that.
Yeah.
It's like you see somebody who's like this, and then
Yeah,
like,
yeah.
Or my favorite of those is sometimes they have like Halloween stores. They have one where it's just like an old person that's sitting there.
Yeah.
Change your head.
It's
That goes. Yeah.
Yeah.
I'm not sure. That might be how they work. So we have here. I have here two polarizers. Now you can see over here, the light's pretty much going all the way through. And when I put this light here, or when I put this polarizer here, now all of a sudden only some of the light's going through. About half the light's going through because I've got the polarizer in there. Now, if I put this other polarizer in front, you can see it's still just about as bright because I have my polarizers oriented in the same direction. What's going to happen if I have light coming through the first polarizer that's polarized this way, so polarized in a plane vertically, and then I switch this one to only allow light going through horizontally. Let's see. I'm going to take this out. All I'm going to do is just rotate it so that now it's at a 90-degree angle. Let's see. So before, I was getting light like this. I was getting a little circle over here. If I rotate it at a 90-degree angle, you can see it goes away. Light? No light. Light? No light. So I'm going to put this here. So right now, I'm getting pretty much no light coming through. Somebody have that other polarizer? I'm just going to steal it for a sec. Turn the lights on up here. Nope, that's not lights. Okay, so what's going on? Put more light in here. What's going on? Is I have a light source over here, and I have a polarizer like this, and the light coming out of the light bulb is unpolarized. Unpolarized light. My polarizer, this is light, this is polarizer, my polarizer will make it so that when this light comes through the polarizer, it emerges on the other side with polarization in only one direction. If I put a second polarizer there, let's say I put that polarizer at an angle. If I put a second polarizer there, well, not all of the light is going to make its way through. So I'll put that at an angle. So here's my polarizer. If I put this at an angle, not all the light is going to make its way through to the other side of the polarizer. Because not all of the light is pointing along that angle. Most of it's, all of the light coming in is up and down, which means only a certain component of that vector pointing up and down is going to be pointed along this angle. If I make it a 90-degree angle, then what you'll see is that none of the light makes it through. Because now, the light coming through the first polarizer is polarized on the y-axis. The light coming through the second polarizer wants the light to be polarized along the x-axis. Since there is no light along the x-axis, it's just going to be completely dark over here. But all I have to do to change that is if I just move my polarizer around, I go back to 0, you can see I can go between light and dark just by switching the angle of this.
So polarized sunglasses, do they have just one polarizer, or
They have
do
polarization.
two that are just not perpendicular, like one up and down and one kind of
I believe they have one polarizer oriented in a particular direction. We can actually do a demonstration of that. But first, I have a quick riddle for you. You might have to save that one for next time. Let's say I put this polarizer behind the other two. What's going to happen to the amount of light that makes it through to this screen? I put this polarizer between these two over here.
Which way is that one polarized?
Let's say anyway. Is there any way I can hold this to get light to come through? Let's see. If I put it, here's my first polarizer. Here's my second. If I put it after the second polarizer, is there any way for light to come through? Let's see. Put it there. I've already blocked off all of the light, so there's no way it's making it through. What if I put it before the first polarizer? So if I put it before the first polarizer, I'm cutting out half of the light. But that doesn't really matter, because whatever light makes it through the polarizer that was here originally is still going to be polarized vertically. And this guy is taking out only things that are polarized horizontally. So this guy passes through anything that's polarized vertically. This guy passes through anything that's polarized horizontally. But since there's nothing polarized horizontally after the first one, there's no light. What if I put it between the two? I put it between. So right now it's blocking out both vertically polarized and horizontally polarized. So what's going to happen if I put this guy between the two at an angle? Let's see. All of a sudden, you get light passing through, even though we're blocking out both polarizations. All right, I'm going to stop here because we're just about out of time. If anybody wants to come up here and play with this, please feel free to. It is kind of fun. You kind of have to see it up close to do it. Yep. There's also polarization, except it is here you're separating the two polarizations rather than blocking them. Yes. Anybody did not get a chance to see the south side, come up and check it out, like I said, it's pretty cool.
Yeah, totally. Just let me know where we're going to get tattoos.